Hello everyone. In today's lecture, we'll be considering the noise in the plant and how we can come up effective controller which will help us to mitigate the noise in the system. So here we'll be using the state feedback controller, what we have done in the earlier lecture. And also we have the simulation results in MATLAB will validate our numerical analysis. So let's start the lecture. So today's lecture is pole placement regulator design for the plants with noise. And these are the topics we are going to cover. Control design for the fighter aircraft, the longitudinal motion, how we can design the controller for this particular case, longitudinal motion with noise. And also we'll have the MATLAB simulation to validate our numerical analysis. So here, we're gonna first define some important term, the measurement noise. The noise are two types. One is measurement noise. This is due to the imperfections in the sensors that measures the output variable. Due to imperfections in the sensors that measure the output variables. So this is basically in the feedback loop, this measurement noise. Because sensor generally we keep it in the feedback loop. So here, if we have the block diagram, we have the summing point here, and this is the reference signal to be tracked. This is the controller. And we will have in the plant to be controlled. Plant output. This is the feedback. In the feedback, we have the sensor. States actual values of the plant, which is going to the sensor. So this is, can I think this is actually measurement noise. The reference signal, this is the output. And there's another source of noise, which is called the process noise. Process noise. This is due to ignore dynamics when modeling the plant. So sometimes we ignore some terms in the system to make our life simple, to make the control synthesis easy. Some complex terms or maybe the values which are very less in magnitude, we don't take consideration those parameters in while designing the controller. But practically those noise also comes into picture. So this is basically acts in the plant. This is in the process noise. So these are the noises scenario we consider while designing controller. So now, considering these two important noise sources in the plant, in the dynamics, so if you consider them in our state space model, so the state space model with noises can be written as x dot equal to ax plus bu plus f xn and y equal to cx plus du plus exn. So as we have done before, we are taking the compact, the most critical case. This example. So here, if you notice, this is we are taking the du part in the output equation, also the noise terms, how they are going to affect the overall dynamics of the system. We are considering everything. So here, this is the state space model of the system equation. And let us define this equation number 1. Okay. So now we are going to some assumption as you have done before. So here assumption is we are assuming the regulator control. So xt, the DGR value we are assuming to be 0. And also we are assuming KKD equal to 0. Okay, since we are assuming there is the reference signal to be tracked 0, so correspondingly we can assume it is 0. So if you go back to our earlier lecture, this how the controller can be designed for this particular system and how these parameters come into picture in the controller, we have explained. In that controller algorithm, we are assuming this part to be 0. Okay. Now, if you, based on this consideration, the control algorithm, we are assuming the controller, we are designing u equal to minus kx and minus kn xn. So here we are taking a new parameter in the controller. This is minus kn and xn, which will help to mitigate the noise in the plant. And this part is going to control the states. So this is, we can assume the state feedback control part. And this is part going to handle the noise in the system. Okay. And now if you substitute this control algorithm in equation, this equation, the state equation. So let us define this is equation number 2. Okay. So if you substitute this equation 2 in our state equation, the x dot dynamics can be written as x dot equal to ax minus bkx minus bknxn and plus f xn. Okay. And if you write in compact form again, a minus bk into x plus f minus bkn xn. Okay. And we can write also in more simplified form. So as we have done in the previous lecture, that this part actually augmented matrix, or instead of a minus bk, we can write ACL, the closed loop augmented matrix. Here we are having the controller part. If you notice, the controller part also coming in the picture. And we can write x plus bn xn. So here ACL equal to a minus bk and bn equal to f minus bkn. Okay, so this is the controller parameter going to handle the noise, and this is the controller parameter going to handle the regulator problem. So here xn acts as the input vector. Xn here acts as a input vector. Practically, it is difficult to predict the values of xn, but we are having some approximation xn for designing the noise coefficient matrix. So now, so this is the overall idea how we can design the controller if there's a noise and how the controller can be designed as a controller for the particular system. The system. Now we'll take example, we'll validate this problem. This example is let me define the problem. Consider a fighter aircraft whose longitudinal state variables are normal acceleration, which is meter per second square, pitch rate, which is radian per second, and elevator deflection. Elevator deflection, which is radian. Okay. Based on the deflection of the elevator, we can come up the torque to the system. So while here we are assuming input, while input is desired elevator deflection. Desired elevator deflection. So this is our input to the plant. Now the plant dynamics is written in this form. So where A matrix, we are having minus 1.7. This is 50 to 60, 0.22, minus 1.4, minus 32, 0, 0, minus 12. This is the X system matrix, and the control matrix is given to us minus 272, 0, and 4. And if the noise coefficient matrix, if is given to us 0.02, 0.1, minus 0.0035, and 0.004, this is 0. So this is the noise coefficient matrix, and the in the output equation, C is given to I, identity matrix, and D equal to 0, and E equal to 0. So these are the values given to us. So in output equation, so if you write in state space form, we are getting x dot equal to x plus du plus f xn, and y equal to simply cx. So this is the equation, overall equation for this particular example, right? Now D and E are 0, and desired pole locations, desired pole location given to us, desired closed loop poles given to us is equal to -1 plus minus I, and is equal to -1. So if you notice here, this is the 3 cross 3 matrix. So characteristic equation is supposed to get the order of 3. And if you get the characteristic equation from these poles, also you will get the third order characteristic equation. Right. And also the noise vector given to us, noise vector given to us, xn equal to 10 to the minus 5 minus 2, 10 to the power into minus 2 into 10 to the minus 6 and this transpose in the vector form, and sine 100 is the frequency omega. Well, so this is the noise level acting in the system. So we need to design a controller that such that there is minimum effect of noise in the state responses. So this is our objective. So we have to design a controller so that the minimum effect of noise will be in the responses. For this is our problem. Now we will solve this problem. Then we'll have the MATLAB code for this particular example. Solution. So before we proceed to the controller design part, first we have to check the system properties, whether it is controllable or not. So these are the fundamental or basics we have to test for this particular system before we go to the control design part. The first part is we have to check the eigenvalues of the system. So we can check the eigenvalues or there is a command in the MATLAB. So I'll try to use MATLAB command in this for this particular example because the system is quite big system. So if you go all the derivations, it will be quite tedious. So we are going to use the MATLAB code for this particular example. So there is a command in MATLAB, and it is called DAMP. DAMP. If you use this command with some matrix A, it will provide natural frequency, damping, and the damping ratio actually, and poles. The poles. The poles are also the roots of the characteristic equation right here. So for our particular example, DAMP, if you write A matrix, our A is matrix here, which gives this matrix, and if you enter in MATLAB command, so we have output, so natural frequency, damping ratio, and poles. So we are getting 4.87, 1 minus 4.87, and natural frequency 1.77 minus 1 and 1.77, and the last state 12, 1 and minus 12. So here, if you notice the pole locations, in this case, there is one pole in the right hand side of the S plane. So this is making the system unstable. So this is unstable pole. So we need to design controller because the system is not stable. So we can say here, we can write here, A is equal to 1.77 is an unstable pole. Okay. Now we'll go to the next part. System is unstability check. Now we have to check whether the system is controllable or not, whether we can control the system or not. So for that, we need to check the rank of the matrix system. So we are having here our V's given to us is minus 272, 0, 14, transpose, and CI, it's given to us 3, B equal to 0. So I is basically I3 means we have 1 0 0 0 1 0 0 0 1. I need the matrix. Now in MATLAB command, if you write R equal to rank of CTRB A comma B. So if it is, since the system 3 cross 3, so we're supposed to get the rank 3. So if you enter in the MATLAB command, the output we are getting R equal to 3. So the system is full rank and it is controllable. So the controller, what you're going to design, it will affect all the states in the system, right? So here, if you notice here, this is basically CTRBAB. It will give you the P matrix. If you remember, P matrix, P equal to B, AB, A square B. So automatically with this command, CTRB will come up with this matrix, and we are finding the rank of this P matrix. Okay, so it is 3. So it is controllable. Now we can use another command to find the control parameters. If you go back to our previous lecture, we had the 2 characteristic equation, and you can comparing the characteristic equation, we can find the control parameters, right? So here you can use some command in MATLAB, you can find directly the control matrix. So our V is given to us, desired poles, V given to us -1, I, and -1 plus I, and -1. So if you look this pole location, these are stable because all poles are in the left-hand side of the S-plane. So if you, in the MATLAB command, in MATLAB, if you write K equal to place A comma B comma B, then it, and if you enter it, it will give you the closed loop, sorry, control gain parameters. K equal to, it will provide 0.006 minus 0.0244 minus 0.8519. So this is the control parameters K1, K2, K1, K2, K3, which is going to control the 3 states. Right, 3 states means these are the states. One is our acceleration, normal acceleration, PC rate, and elevator deflection. Right, 3 states can be controlled using these 3 control gain parameters. So now we are having the control parameters, and also we are having the A and B matrix, so we can find the augmented matrix, right? So now we'll find the augmented matrix. Augmented matrix. This is, we know, ACL equal to A minus BK, right? Now, if you put all the values, what you have found in the 4 steps, so our augmented matrices comes out to be minus 1.526, 43.36, 28.28, 0.22, minus 1.4, minus 32, and minus 0.008, 0.34, and minus 0.07. Right. This is the augmented system matrix. So we have done the first part of the controller. So first part of the controller. Now we're going to start the second part, how to control the noise. So second part. So here, if you notice, we need to find the BN matrix, which is F equal to, sorry, the Bn. So for noise controller, we need to find Bn equal to F minus Bkn. This you already have found. This is here, right? So here we have. So now we can substitute all the values what we have found. So F already given to us in the example. F is given to us here. This is F given to us. So you can use that F here. So we can write 0.02, 0.1 minus 0.0035 and 0.00400, right? And minus, we can use minus 272,014 and Kn, we are assuming Kn1 and Kn2. So these are the control parameters which is going to control the noise. So finally, we are having the matrix here 0.02 plus 272 Kn1, 0.1 plus 272 Kn2 and minus 0.0035, 0.004 and minus 14 Kn1 and minus 14 Kn1. This Kn2. So this is the matrix of F minus Bkn, right? So now, what we're going to do is we need to find the K1 and K2. So what we're going to do is we'll make these parameters to 0. We'll make this parameter, we can take make the largest parameter to 0. So if you use this two parameter, we can find the K1, Kn1 and Kn2. So what we're going to do is making first row to 0, we can find Kn1, we can find minus 0.02 divided by 272 and Kn2 we can find minus 0.1 divided by 272, right? And considering these values, if you consider these values in this matrix, so we can find Bn. So Bn, the first row will be 0. That is obvious because you already assumed to 0. So F minus Bkn, we can write 0 minus 0.0035, 0.004, 0.001 and 0.0051. This is the Bn. So this is the Bn matrix. So this is Bn matrix we are getting. Now, if you notice carefully here, so okay, this means we are always going to have some effect noise in the closed loop system, because if you notice here we have the values of which are the non-zero values, so some effect are there in the system. But let's see, while we'll be doing the MATLAB code, we can get the better picture how it is going to happen. So now we have Bn and we have ACL, so we can find the overall state space model. So let's work on this. So now we have, so we can use the MATLAB command, a state space LTI, linear time invariant, can be designed by the command SS. Okay, this command we can use in MATLAB. So this is, if you consider, okay, I'll come back here again. So if you notice this system matrix, so this is closed loop system, this is basically closed loop system, right? Because everything, if you notice here, Kn is the controller, and based on this, this is the augmented matrix, and this is here the another augmented matrix for state, and this is the augmented matrix for xn, right? So now, this is the whole equation is actually in closed loop form because the controller already in the loop. So now we can come up the closed loop state space model. So here, let's write in the MATLAB command is this system closed loop, we can write equal to SS ACL BN CD if you substitute, because in this particular case, our D part is 0 and C is identity matrix, and BN already we have found here, and ACL already found before. So if you use these matrices in SS command, we can get the output. So if you in the MATLAB command, if you enter it, so we'll get, so output will be this quite big equation I'm not writing here. Output as continuous time state space model of the closed loop system. Okay. Now, how we can see the response of the system? This is a very important part. So we have the closed loop system where we have controller is inside, controller included in the system. Now we'll see how we can get the response, whether the response is stable or not, because controller already designed the closed loop model. So in the system MATLAB, if you use some command, this command is called in MATLAB. There's a command LSIM. So this produces the state response from the given or measured data. So how can I use this command? Let's work on this. So here in MATLAB command, if you, okay, instead of this, I can take the MATLAB code and result. So that will be useful for you. So what I can go is, this is the MATLAB result of this particular example. The full code is here. So let's work on this. Yeah. So the full code for this particular example is given. So here, if you notice here, the A matrix is defined, B matrix is defined, C matrix is defined. So this is basically the problem what we have given in the system. So then we have used the DAMP parameter, which will provide the natural frequency, damping ratio, and poles, right? Then we are checking the controllability of the system, and it is found to be system is controllable. Then we are finding the closed loop function for Bn. So this is how we found. So this is the Bn function. This is how we are finding. Then we are finding the system. Then again we are checking, because if you notice, we have the system x dot. We have the system x dot equal to we have ACL x plus B in xn, right? So now here what we are doing is we are checking the controllability of this system. So this is what you are doing. Controllability of the system with noise. Okay. Then we are simulating the system, simulating for 0 to 5 seconds with sampling time 0.01. And this is the noise given to us. This is the noise, this part, Xn is given. And then we are finding the state space model of the overall closed loop system. And we are using LSIMC command here. And we are simulating the system, closed loop system, what is here. And we are giving the this noise in the system. And we are finding the response of the system over time. So if you notice here, you can see this, the noise of the system has very less effect on the states. So we have the 3 states, AM and phase rate and elevated deflection. So you see the value is 10 to the minus 9. The effect of the noise is quite less in the overall response of the system. But as a control engineer, if you can increase the, suppose in this particular case, we have chosen the, so here we have chosen the desired eigenvalues or the poles are this level. But if you want to increase the, if you put instead of this, if you put, suppose for example, in the present scenario, these are the pole location, for example. But if you can make, suppose here, here, or here, sorry, or maybe here. So if you can choose your pole like this, you can get better response. But the problem is you need more control authority in the system. So you should have the proper, you can get better result, but you need to apply more control. So to apply this amount of control, it is quite challenging for the onboard system because we have some control, some saturation, right? We can't use as much as we want. There is some limit. We have to look at those things. So that's why in the present scenario, we have those are the desired eigenvalues, and based on that, we have designed the controller, and this is our response. So from this example, the takeaway is how we can design a controller which help us to mitigate or to try to mitigate the effect of noise in the system. So I hope it is useful practically how we can design the autopilot for your aircraft. So let's stop it here. We continue from the next lecture with some new topics. Thank you.